My name is Eldi Lazaro, first year PhD student at the Atlas Institute. Together with my co authors, we have contributed on the paper I'm presenting today, exploring biofoam as a material for tangible interaction. Our research rests on two pillars of related work in the HCI. First, the growing use of bio based materials with growing programs of sustainable and biodesign. Second, design reflections that consider materials as actively shaping the design process and imagination. Drawing from the materials experience framework, we highlight the intrinsic sensory affordances of biofoam as an entry point to analyze interactions with the material. But first, let's start describing what is biofoam. Biofoam is a foam like material that is water soluble, low density, airy, flexible, similar to foams used in packaging and bedding, and it can be made conductive. Our motivation for exploring this material relies on adapting and thinking with the materials in the context of HCI. We highlight the particular affordances biofoam offers for tangible interaction, recyclability, and fabrication processes. Our core contributions consists of the introduction of this biofoam material to the HCI community, as well as research guidelines of how it can be meaningfully manipulated as an interactive material. Furthermore, by analyzing and understanding the life cycle of the biofoam, we aim to guide our material investigation and seek to answer the following research questions. How can the biofoam recipe be tuned to obtain new forms that can be leveraged in human computer interaction design? And what design opportunities emerge when we use biofoam in HCI applications? To answer these questions, we started with a material experimentation phase. There, we explored adding multiple ingredients on the biofoam based recipe to tune its attributes such as color, aroma, texture, water permeability, or conductivity. During this process, we found that pine tree sap, for instance, increases the water permeability of the biofoam, or that dish soap not only acts as a foaming agent in the base recipe, but also adds aroma to the final biofoam sample. Furthermore, the biofoam density can be tuned by varying the whisking time, and we can achieve conductive biofoam pressure sensors by incorporating stainless steel fibers on the recipe. After producing several different kinds of biofoam, we became increasingly interested in the capacity of the material to squish and slowly recover to its original shape. First, we studied this qualitatively by manually stretching, squeezing, twisting, and gradually applying pressure on the samples. Then, we considered how this quality of the material could be used for pressure sensing, and therefore began to conduct more systematic characterizations, such as a compression test. The results of this test show that we can accurately predict the force needed to compress up to 72% of the biofoam. Through making a variety of biofoam recipes, we noticed that the properties of biofoam and the fabrication techniques used to shape it mutually influence one another, forming a core dialogue when designing with biofoam as a material. Across our experiments, we used a combination of craft and digital fabrication techniques to shape the material. The biofoam can be molded, layered, extruded, sewn, embroidered, pleated, cut, and laser engraved. We provide detailed instructions for our most commonly used techniques, molding, extruding, and layering in Appendix B in our paper. Combining the various fabrication methods with the material's tunable properties allowed us to imagine several applications for biofoam in HCI. Initially, we created biofoam wearable accessories that we called chameleon accessories because of their ability to change color when they are worn. They have biocompatible thermochromic and photochromic pigments embedded on the biofoam. The collection includes one necklace, two bracelets, two rings, one pair of earrings, and one face mask that respond to heat and UV light. The waste generated during the accessories prototyping process was recouped at its end of life to make new biofoam and accessories. Lastly, we created four sensitive resistors that we characterized and envisioned future use in tangible interactive objects. We found this application particularly compelling as the compression interaction is built into the foam. Furthermore, the compression conductivity and the recovery time can be tuned simply by altering the recipe, and the form of the sensor can be also customized by molding the mixture into specific shapes and textures, lending to further play with interaction and design. At the end of life, all conductive biofoams can be dissolved in warm water since its main ingredient is gelatin. Using a magnet, we can collect the stainless steel fibers from the dissolved biofoam solution easily. After harvesting the conductive stainless steel fibers, they can be reused and spun back into a new conductive yarn. We aim to advocate for biofoam as a tunable material for tangible interaction. Materiality was a design consideration that stood up during the fabrication process of the biofoam. Various ingredients, materiality, and properties at play made us question design considerations of durability, malleability, fragility, density, viscosity, biodegradability, and so on. These influenced reflection beyond the realm of tangible experience towards questioning other sociocultural and environmental considerations, such as how our ingredients are sourced, the distances they travel to reach our lab, or the potential impact on people and our planet the biofoam could have at its end of life. Another design consideration was temporality. We compared the temporality of fabricating the biofoam to the temporality of cooking. Design considerations of tunability, the ability to be modified, accessibility, which is easy to find, and replicability, which is easy to make, accompanied us throughout the fabrication process, as they do when considering making a new recipe for dinner. While bio-based materials such as biofoam present opportunities to support sustainable design in such prototypes, we see opportunities to design with foam materials beyond instrumenting their innate functional properties, and rather tuning their built-in material affordances like squeezability that invite tactile interaction. Furthermore, we can consider the process of making or cooking the materials and or their end of life biodegrading as sites for further interaction and engagement. For instance, how can we design with biofoam's ability to dissolve in water and use it as interaction? To this effect, this material integrates well into a growing discourse within HCI on themes of decay, obsolescence, living materials, and material drift. We believe that by focusing on the biofoam's entire life cycle in design, current interaction designers' attention could shift from how to shape the material from a human centric approach to a more material centric approach by focusing on the material's temporal aspects, making it simpler to trace the relationships between different materials and the dimensions of acknowledged fabrication processes and practices. Finally, we found that fabricating the biofoam and using it as an interactive material offered unique sensory experiences. For instance, cooking provided a natural sensory rich experience that helped us learn and develop a greater understanding of the material through an embodied experience. By interacting with the cured foam samples, we realized they each possessed their own individual sound, smell, and tactile qualities, shifting our attention from the overarching scenarios of use to attending to the microsensory details. Our core contribution in this paper consists of the introduction of this bio based material to the HCI community, as well as researched guidelines of how it can be meaningfully manipulated as an interactive material. Thank you for your attention, and please feel free to reach out to me if you have any questions. Bye.